Hey everyone, so today we're going to talk about resources on Earth and how they relate to geology, specifically energy and minerals. So most of this lecture is going to be about energy resources. The minerals, I know we spent a lot of time about talking about minerals in the beginning of the class. So just the end of this lecture will touch on Earth's mineral resources. So most of what we'll talk about today is our energy source types. So we will talk about the types of resources available on Earth, including oil and gas and coal. And we'll talk about the difference between oil and gas versus coal, fossil fuels, and some of the issues that come from society relying on fossil fuels. Then we'll talk about ore deposits and mineral extraction. So to start with, energy is the ability to do work, and a resource is a material that can be used. So when I say an energy resource, it's something that can be used to create energy. So energy to make something. When we talk about renewable energies, a renewable energy source is a natural resource that can replenish itself within our human time scale. So something that replenishes frequently enough that we can rely on it to continuously be there, even when we use it up. Something that is non-renewable does not replenish itself. So either it doesn't at all replenish, no more is being made, or it takes way too long for that resource to replenish when we are using it up too quickly. So it's not something that we can rely on because it won't be there. With a non-renewable resource, it will run out. Something that is renewable will not run out. So there's two types of resources that we're going to talk about today. Like I said, energy resources. So this is how we make heat and electricity. This is how we move things. Mineral resources are, we use mineral resources to make things. We'll get to those at the very end. So the energy resources on Earth, we get energy from the sun, we get energy from gravity, we make energy from photosynthesis, plants. There's energy from chemical reactions. Some happen naturally, some happen because we're forcing it. There's energy from fossil fuels, so burning fossil fuels. Energy from nuclear fission, so that's one of the chemical reactions that we make ourselves. And there's also energy that we can get from Earth's internal heat. So we'll get into these. The resources on Earth that we use by percentage, this graph is a couple of years old. I think it was published in 2016, but things haven't changed very much since then. Most of the energy, the resources that we use on Earth are from oil, and second and third place come in coal and natural gas. So there's not very much of our energy usage going towards renewable resources. We are using mostly non-renewable resources. So we're going to talk about oil, natural gas, and coal quite a bit today. So that brings us to fossil fuels. So fossil fuels are a natural fuel, so a natural resource that is formed from living organism remains. So it takes something on the scale of millions of years to form these fossil fuels, and they can be burned to produce a huge amount of energy. So fossil fuels create a large amount of energy, but they are non-renewable resources because it takes millions of years to form. So that is definitely longer than a human lifetime. So if we use up all of the fossil fuels on Earth right now, for example, it would take another 1,000,000 years to form more fossil fuels. So the main fossil fuels are oil, natural gas, and coal. So oil and natural gas kind of go together. They're very similar in formation. Coal is quite different. So we're going to talk about all three. And then you might hear the word hydrocarbons. A hydrocarbon is a chain of molecules that's made of hydrogen and carbon. So organic chemicals have hydrocarbons. So all of these fossil fuels are made of hydrocarbons. So first, we'll talk about oil and natural gas and how they form, and then we will get into coal because it's completely separate. So oil and natural gas are actually formed from dead algae and plankton. So when these little cells of our algae and our plankton, they die in the ocean, they will sink down to the bottom. When they sink down, they will become part of the ocean floor. So they mix with the clay and silt and maybe sand at the bottom of the ocean, and they will stay there, hopefully, because in order to form oil and natural gas, you need to have that layer of organic material. You need that layer of algae and plankton bodies. And if the water is moving too much, so if this was a really active area in the ocean, those cells wouldn't stay. So those little phytoplankton and algae, they wouldn't stay on the bottom. They would get blown away. So you would never have oil and natural gas forming in a highly active area. So you want somewhere that the water is very still so that all of these small particles can actually settle out of the water and sink to the bottom and then not be disturbed. So generally, for oil and natural gas formation, you also want oxygen poor water. So oxygen poor, meaning there's not a lot of oxygen in your water, which means there's not a lot of other living things around. So what happens is you're not going to have a lot of decomposition, and also you're not going to have a lot of other organisms. Because if there were other things swimming around, they might feed off of these phytoplankton and these algae, and they wouldn't be able to accumulate here. But if you have more of this oxygen poor, the algae and the phytoplankton are able to actually settle to the bottom, mix with that clay, and get buried and become a nice layer of that organic material. So you want oxygen poor water and still water, or very, very, very slow moving water, for all of this to form a nice layer. And then when it becomes a layer, it's a sedimentary rock, we know, because it's settling out, and then it's forming a nice horizontal continuous layer. We would call that a layer of black shale. So it would be organic black shale. So it's a shale, but it's made of dark organic material. So all oil and natural gas comes from a layer of black shale, which is made of algae and phytoplankton. So that black shale is considered the source rock because that's where it comes from. That is the raw material in terms of that is the layer of rock that is made up of the organic material. So in order to produce your oil and your natural gas, you have the layer of source rock needs to be buried. So oil is a liquid and gas is a gas. So this shale isn't going to help you very much. So this layer of black organic shale is a rock layer. It's not very useful. So what we need is we need this rock layer to be buried, and we need it to be buried very deep so that it warms up. So once that layer gets to be about 50 degrees Celsius, which is going to happen anywhere between 2 to 4 kilometers in depth, so it gets buried over time. This is because more and more sediment layers or sediment beds will form on top. So eventually, once it gets warm enough, chemical reactions will begin to occur, and this rock layer will start to turn into what we call kerogen. So kerogen is sort of step one in the process of forming oil. So the first reactions that occur when this organic shale becomes warm enough, we have that organic shale turning into kerogen. When you hear oil shale, it is not oil, and it's not quite shale. It's actually shale that has started to turn to kerogen. So you have shale and kerogen within your oil shale. You actually don't have any oil yet. So naturally, you wouldn't be able to get any oil out of oil shale because it's technically still rock. You don't have any oil there yet. So what needs to happen is that oil shale, so your shale that has now started to turn to kerogen, needs to warm up even further to actually create oil and natural gas. So once that oil shale warms up to 90 degrees Celsius or more, that kerogen is going to break down and create those hydrocarbons that we need for oil and natural gas. So both oil and natural gas are produced from kerogen molecules once they get warm enough. So how do we warm up our oil shale to over 90 degrees Celsius? You betcha. We bury it even further. So once this layer is buried, so you'll notice in these pictures, our source rock is getting deeper and deeper down towards the center of the Earth. And we know from our geothermal temperature gradient that the center of the Earth is warmer than the surface. So as this layer gets pushed further and further towards that very warm center of the Earth, or really towards that warm mantle material, because this is still all in the crust, once we reach about 150 degrees Celsius, all of the oil will turn into natural gas. So after about 90 degrees Celsius, you're going to turn all of that kerogen into oil. If it gets even warmer to the point where it's up to 150 degrees Celsius, that oil is going to break down into natural gas. So it's an actual gas. If it's over 250 degrees Celsius, so very, very deep down in the crust, very, very warm, all of that carbon material will actually turn to graphite. So you remember graphite when we did our soft mineral identification box. It's the dark gray one that is the lead in your pencil is graphite. Got black stuff probably all over your hands. So that was oil and natural gas that was way, 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 way too hot. It was under too much pressure under the surface. Under the crust. So it actually turns to graphite. So oil itself only forms in a very specific window. So only between 90 and 150 degrees Celsius can we form oil. If it's too cold, so if it's less than 90 degrees Celsius, we're just going to have that oil shale. It's going to be the shale with the kerogen, but we won't have that kerogen breaking down into oil. If it's warmer than 150 degrees, that oil is going to be all broken down into natural gas. So oil we really only find forming in the top 6 to 9 kilometers of Earth's crust. So here's a nice image, sort of step by step. This one's from our textbook. So we have our phytoplankton and our algae accumulating in our oxygen-poor and still water. That layer of sediment, our source rock, is going to sink down. It's going to sink down even further. Once it gets between 90 and 150, the kerogen will break down into oil. Oil, remember, is a liquid. Liquid is less dense than solid, so that oil will start to rise up through the solid material. It moves rather slowly because it is rising up through layers of rock, but that liquid layer, so as this layer turns into a liquid oil, it's going to rise up through the rock layers above. So how do we get this oil? It is under the ground. Clearly it is deep down enough to be between 90 and 150 degrees Celsius. How do we actually get it to use it for energy? We have to find what we call a reserve. So a hydrocarbon reserve is a supply of oil or natural gas underground. So an oil reserve or an oil field, you might have heard of an oil field, And then we also have a gas reserve or a gas field. So that is just an area where there is a lot of oil underground, sort of trapped. So when we think about actually retrieving these resources, there are two types we call conventional reserves and unconventional reserves. So conventional reserves are the ones that we can pump oil rather easily from the ground, so we can drill in and get the oil out. This is how we've been doing it for a very, very, very long time, is getting oil, getting resources from these conventional reserves. Unconventional reserves are rather new. So these are areas of these resources that were not previously usable, but due to technological advances, due to updated technology, our abilities to retrieve oil and natural gas from these reserves have increased. So we're actually able to now get oil and natural gas from unconventional reserves, which wouldn't have been possible 20, 25 years ago or earlier. So let's look a little bit about conventional hydrocarbon systems first. So conventional meaning this is the way we've been doing it. It's the easy, more, not easy, but simpler way to retrieve oil and natural gas. So this is drilling into a reserve of oil and natural gas. So we can't drill directly into the oil shale because oil shale is not actually oil. We need to find reservoir rocks. So reservoir rocks are the rock that the oil has risen up into. So the oil from our layer of oil shale rises up, remember, because it's a liquid, and what it rises up through is what we call a reservoir rock. So the oil and the gas actually exist in between the grains of our reservoir rock. So in this picture of a rock with high porosity, it means there's a lot of space within the grains. Here, this has very low porosity. There's not as much space in between. So if you were looking to extract oil from a rock, you would want to find a rock like this, which has quite a bit of oil because all of this space could be filled with oil in between these grains. So when you're looking for a reservoir rock to extract oil from, you want something with high porosity because there's a lot of space within the grains to be filled with oil. You also want to look for something, a rock with high permeability. So this means that fluid can very easily flow through the rock. So there's something that, there's a clear pathway. So a clear pathway for that oil to travel in between these rocks. So here, this is not very permeable. Even though there are pore spaces, they're not really connected. So you wouldn't be able to move that oil from one spot to another. So yes, here there are pore spaces. This sort of has a medium porosity, but it's not very permeable in that the oil wouldn't be able to flow, for example, to your drill. Here, we have pore space that is connected. So fluid, like our oil, can actually flow through these pore spaces. So when you're drilling for oil, you're looking for a reservoir rock that has both high porosity and high permeability so that you have a large amount of oil and it can flow easily through that rock. So oil shale has very low porosity and very low permeability. So you're not going to be drilling into the oil shale. That's not going to help you at all. The oil will not be moving. You have to drill into that reservoir rock after the oil has migrated to the reservoir rock. So what happens if we follow this picture here? Here's our source rock. So here's our black shale, our organic black shale. Eventually, over time, this is compressed and warmed up, brought further to the center of the earth, towards the center of the earth, deeper within the crust, and our oil will start to form. So that oil and natural gas will start to form. Since it's liquid, it's going to rise up, and it's going to get stuck eventually by a seal rock layer. So we call a layer a seal layer if it's something that the oil cannot travel through. So reservoir rock is a layer that the oil is able to travel through. The seal rock is something that stops it. So the oil actually isn't able to travel up through every layer of rock. So when it reaches a seal rock, it's going to pool. So it's going to start to pool here. It's all going to rise up until this seal rock. So then later on, we can pump down and drill into that reservoir, which is within or right above the reservoir rock and underneath our seal rock. So when we are actually drilling for oil, you're not looking to drill into the source rock. You're looking to drill into the reservoir that is above. If there is no seal rock, so if there is no layer to seal that oil reserve, it will actually reach the surface. So that is called an oil seep. So this is somewhere where oil literally seeps out of the ground and reaches the surface. This is not something we can generally extract from because it never builds up a reserve like this. It never builds up a pool or an area that we can pull oil out of. It's just going to continually come to the surface and not in a way that is very usable. So seal and trap. So the seal rock, I should say this here, the seal rock makes what we call a trap. So the traps can be formed in many different ways. So this first one here on the top left is called an anticline trap. So we know what an anticline is. It is when we have a fold in our rock in this direction, right? A syncline would be the opposite. It would be more like a U. This one is an upside down U or an N. So our anticline trap, our source rock here, the dark gray, would form our oil. The oil will rise up through the reservoir rock and it will get stuck underneath the curved seal rock. So because this has been folded, the oil is going to, even if the oil is formed over here, it's going to rise up to the seal rock and then it's going to try and go to the highest possible area. So the oil is going to move as close to the surface as it can underneath that seal rock. So the trap, the amount of oil, that reserve of oil, will actually accumulate in the highest part of that fold. So in the top part of that anticline fold there. So that would be a very good place to put your oil well. Another one is a fault. So if you have a source rock and a seal rock with our reservoir in between, of course, and then we have some faulting. The faulting, what type of fault is this? Giving you time to think. A normal fault, yes, very good. Because this is our footwall, here's the toes, and then the hanging wall is moving down. So very good, it is a normal dip slip fault. Anyway, so we have our oil trap here. And again, this source rock is going to create our oil. Our oil is going to rise up and it's going to move to the highest possible spot that it can go underneath that seal rock, which when there's a fault involved, it will all usually be up against the fault line because the fault is going to cause some friction. It's going to, you'll see how this seal rock is not completely straight across. It's actually been dragged upwards because there's a lot of friction along this fault. So anywhere where you have a reservoir rock that's not perfectly flat is you're going to have that oil trying to get to the highest possible spot underneath that seal rock. So again, it happens here where we have an offset. So here we have a contact between two layers. This would be angular deformation. This is where we have, an angular unconformity, not deformation. We have our source rock. We have our reservoir rock here. So here we have our source rock and our seal rock right against each other. So the oil is not going to be able to seep up at all through this seal rock. So it's actually going to seep out the side. And then the oil that is formed here in our seal rock will rise up in our reservoir rock and then again try and move to the highest possible point. So when you have a pinch out like this is kind of what we're calling it. You actually pinch the oil out between these layers. So if you can find this pocket, again, a good place to put your oil well. And then this is another example if we had a salt dome. So this would be an accumulation of salt underground that has been stripped out of whatever was around it. Again, you're going to have curving of your seal rock. You have curving of your source rock as well. But there's this spot here where this oil is going to accumulate at the highest possible point underneath that seal rock. So the oil is a liquid, the gas is a gas. So they are less dense and that material is going to try to get to the surface as much as possible. So no matter where you are underground, the oil is going to try to move to the highest possible point beneath that seal rock. So it's always going to move to the highest possible point that it can get to underneath that seal rock. And those oil traps are where that oil is going to accumulate because it is trapped by your seal rock. And that is where you're going to want to drill if you're drilling for oil. So here's some examples. You can see a lot of them put together. Here we have our anticline, oil and gas. Here's a fault line that is causing our oil and our gas there. Here's a trap from the different angles. So this is just to show you another version of the figure, not just from the textbook. So now we've found our traps. How do we actually get the oil out? So we use drills, generally, for the most part. Drills a hole down, it pumps the oil out of the trap, and the oil is then stored generally right there on site. So about 30% of oil can be removed just from pumping from the drill. To get the rest of the oil, generally we need other techniques. So mostly drilling facilities will inject water to get the oil to move around, move up towards the drill, or use CO2 to actually heat up the oil or push the oil, move the oil so that we can get it and use it. So oil on Earth, it's pretty spread out, but it is not spread evenly. So most of the oil reserves on Earth are in the Middle East, all around here. Whoop. So we have, here we go. The percentages, so almost half of all the oil on Earth is in the Middle East. We come in third place in North America. There's a good amount up in Alaska and northern Canada. There's some down in the south. We have a little bit here in Huntington Beach. But for these oil reserves, most of what we do now is the conventional drilling. So we use conventional techniques to access our conventional reserves. However, since about 2005, people have discovered how to extract hydrocarbons from unconventional reserves. So this being actually extract from the impermeable or low permeability and low porosity rocks and make it worthwhile. So these are new techniques that have required new understanding and new studies and definitely new technology. So we're actually able to extract not just the oil that's already been created, but sort of the earlier steps. So tar sands, so when the oil is not quite oil yet, but it's on its way. It's more like a thicker, heavier oil. It hasn't fully converted to oil. We can actually extract that and heat it ourselves up on the surface to create oil. And also, we now know how to extract that oil shale and turn it into oil ourselves. So the oil shale being that layer of organic material that has a large percent of kerogen. So it's already started the process, but it isn't quite in the window of 90 to 150 degrees Celsius to create oil on its own. It's not there yet. We can actually extract that, bring it to the surface, and warm it up ourselves to produce the liquid oil. And then we can also take shale oil. We can make shale oil and shale gas from those impermeable layers using fracking. So I'm going to explain, here we go. I'm going to go over what is fracking. So it's a little controversial. So you might have heard about fracking in the news. I'm just going to explain real quick. Fracking is one of the ways that we access these unconventional reservoirs, these unconventional resources. So we would drill, I'm not involved, I keep saying we, they would drill down into the oil shale or the layer of shale and pump water. So the water, they would then cap it up so it would increase in pressure, and they would continuously fill with water to the point where the water is actually going to start cracking the rock around it. So the water will start to make all of these cracks, all of these joints in the rock layers around, and then that would also move sand. So the sand that's also being moved within this water is going to help push these joints apart. So the water, it's under incredibly high pressure. It's actually going to push the sand up into the joints and down into the joints, and then the sand is going to keep, the sand particles will keep those cracks open, keep those kind of prop open the cracks that you've just formed, so you can remove all the water. So now you can pump your water out and allow the gases that are within this rock to actually flow down into your drill hole and then out into, or up into your drill up on the surface. So you're expanding the reach of your drill, so you're not just drilling a hole and gathering what's here. You're actually cracking all of the rock, so you can try and sort of strip everything from this area of rock in terms of everything sort of useful. So it's not the best way to do things. So this is sort of a full picture. So the picture that I had just before is just a zoom in. So if you were looking at the full picture, with fracking, we're actually able to drill below the water table into this layer of shale, organic shale material, cause all of the cracks. They call them hydrofractures because they're fractures caused by water, hydro. And then all the gas, all of that oil and natural gas will seep into the drill hole and then go up to our surface. Not great because there's a lot of potential to contaminate our groundwater. So to contaminate the water that we drink, that we rely on, can be pretty bad if that were to happen. And also sometimes this fracturing creates earthquakes, so there will be shaking up on the surface. If it gets to be too much, if there's too many cracks, you might have some really serious shaking, and you might cause some really serious fractures. Some really, really bad earthquakes can be formed from this fracking technique. So there's a lot of people that are fully against the fracking technique for getting our hydrocarbon reserves. So that is oil and natural gas. Next, I want to talk briefly about coal. It's a bit of a easier to understand process, so I'll go a little faster. But coal is our third fossil fuel. We use quite a bit of coal on Earth to burn to create energy. It's carbon, so it's an elemental carbon mixed with some other minerals and materials. And instead of, like oil and natural gas, which are formed from layers of algae and plankton in the ocean, coal is actually formed from plant material. So plant material, generally a swamp, because we want still no motion so that this process can happen. So we don't want our dead plant material to then be blown away or washed away. It needs to stay in place to actually form our coal. And we also want an oxygen poor environment. So similarly to the formation of our natural gas and coal. So similar situation, however, to form coal, we want swamp vegetation. So leafy vascular plants, not just phytoplankton. So this vegetation will die and it will fall to the ground and it will get buried in a layer. So that is going to actually become a sedimentary layer that we call peat. So peat is the layer of rock material made up of all of this dead plant material. It's usually more than half carbon, and it's sort of the halfway there mark to creating coal. So we have our leafy forest, swampy area up here. Everything that dies will fall down to the ground. There's not a lot going on, so there's not a lot of oxygen, so there's not a lot of decomposition, so it's able to stay. Eventually it will get buried by other layers of rock here. So here we have our leafy coal, it's getting compressed. Our leafy peat, it's getting compressed. It's going down towards the surface of the earth, towards the center of the earth as our layers form on top. Over time, it's compressed even further. It's pushed even further down into the crust, further from the surface, allowing that peat layer, the dead layer of organic material, to actually condense and form into what we call coal. So here is a really cool picture of some exposed coal beds. So these beds have since, they would have formed way, way down. They have since been uplifted and eroded so we can see the layers of coal there, which is very cool. So we know from this image here that there used to be a swamp on top of this rock layer. So here we have this dark coal layer, and here we have another layer of very, very dark coal. To mine coal, there's a couple different ways. Well, really only two. Strip mining and underground mining. So strip mining is when you find a layer like this and you dig down to it. So it's closer to the surface. You actually just dig down to the layer and you pull all the coal up. This is better when we know where the layer of coal is and it's relatively close to the surface. An underground mine would be if you were mining a layer of coal that's even further down in the crust, and it's too much work to remove all the layers on top. You would actually dig down and have underground channels getting to this layer of coal and bringing the coal up to the surface. So our coal on Earth, again, is still pretty spread out, but not evenly spread. So the black shapes on here are where we have coal. The red is where we have a layer that is going to eventually become coal, but it takes a very long time. Remember, these are non-renewable resources, so these do not replenish within our lifetime. So we are number 3 in coal reserves in terms of continents. It's pretty evenly split between Asia, Pacific Asia, Europe, and North America. So those are our fossil fuels: coal, oil, and natural gas. So I'm just going to really quickly go over a few other sources of energy that we use on Earth. So the first being nuclear power. So we're actually able to cause nuclear reactions, hopefully very contained in a safe environment, that we're breaking down large atoms. So there's certain atoms that can be broken down, and when they are broken down, they create a large amount of energy. We call this fission. So from nuclear fission, we can create a huge amount of energy that can then be used at a nuclear power plant to heat water, and that water will spin a turbine. That turbine will collect our energy. So nuclear power is usually used to spin a turbine using steam, and that can create a huge amount of energy for us. Another type of renewable energy is geothermal energy. So this is using the heat from the center of the Earth. So we're actually using Earth's internal heat to produce energy for ourselves. So using really hot groundwater, we can actually take steam, or sort of take the heat, use the heat of that hot groundwater to create our energy. This again will generally spin a turbine. So we'll somehow harness the heat from the center of the Earth to create steam and spin a turbine, and then store that energy that's created from that turbine. So this is often done where we have a higher thermal gradient, meaning a region of volcanic activity where we know we have hot magma closer to the surface. So because you know that it's actually going to be hotter closer to this magma, so it's going to be hotter over here than it would be way over here where you're away from that magma plume. So you're going to want to use geothermal energy where you know you have a source close by. So somewhere that you know that there's magma close to the surface, like somewhere with high volcanic activity, is where geothermal energy is the most useful. There's also biofuels. So there's certain things that can actually use crops, so things that we can farm to create energy. So vegetable oils, grasses and algae, and then often corn and sugar can be used to create energy. So this is renewable because we can continuously farm corn and sugar and grasses and vegetables to continuously create and replenish our biofuels. Hydroelectric power is getting pretty popular. So this is where we actually use gravity and water to turn a turbine and create energy. So this can happen in a river where you have moving water. This can also happen in a dam. People will install hydroelectric turbines to actually collect the energy that water can generate just as it's flowing downhill, just as it's flowing using gravity. So hydroelectric power can be very, very, very powerful. We just have to know where to put it. So wind is very similar. So instead of water turning a turbine, we have wind turning a turbine. So this is a great one. Totally renewable, very carbon free. We have a lot of wind power, a lot of wind turbines in California, which is very, very, very cool. Some of the arguments that I've heard against wind energy is that they look bad, they're loud, and they kill birds. I think they look very cool, actually, especially when you see like thousands of them in a field together. They are not loud, and the percentage of birds that they do kill is incredibly low. But there are still a lot of arguments against building wind farms. especially on the East Coast. California is one of the largest users of wind energy and wind power in California. In the U.S., which is really, really cool. The last, of course, renewable energy is solar energy. So the sun is not going to shut off for another 7 to 8 billion years, so it is very, very renewable. It's a huge source of energy, specifically here in California, where we get a lot of sunlight. It can be pretty hard to use, though, specifically because the sun is only out for half of the day. So we only have sunlight during the day, and especially seasonally, depending on where you live. Many places don't have as much sun in their rainy season. And it can also be really difficult to convert solar energy into other types of energy. So with your solar panels, you have to also have a really great battery so that you can collect solar energy during the day, during the sunny season, and store it up to then be able to use, say, at night or use on a cloudy day. So that is right now sort of the limitation of solar energy. I think solar energy is kind of exploding, which is great. I'm so glad to see so much energy, so much solar energy being used. But as of now, it's great for individual buildings, but not so much to run an entire city. It's not as reliable as it will be, I'm sure, in a few years to come. Elon Musk, I think, is working on it. He and Tesla will figure out the best way to store our solar energy. I do think this is going to become more and more and more common and popular in the next few years. So hopefully, anyway, our renewable sources of energy will become more popular because we do have some issues relying on oil. So the oil age, they say, that we are in now will span about 300 years, which means the non-renewable resources of oil and coal and gas are really only going to last us about 100 more years. We've been using these resources with at an increasing rate, and we are not discovering any more. So we pretty much know how much we have and how long we have until it runs out. So they say we have about 100 more years left until we are short on oil to the point that it's going to be detrimental. So I'm glad to see this shift to our renewable energy sources is happening now. It should continue, in my opinion. So what are we going to do in the future is the big question when we don't have oil, when we don't have natural gas to rely on. That is something that needs to be figured out soon. There's also some other environmental issues that come with our non-renewable energies, which are oil spills. So oil spills are particularly horrible in the ocean because that oil can be incredibly difficult to clean up, as well as acid mine runoff. So all the acid runoff from the mined material can get into our water system and turn our water into, it'll be too acidic, so like acid rain, but it will be acid river or acid stream. And then also with our burning of fossil fuels, of course, creates so much air pollution. So we do not want any more air pollution. Certainly not. We don't want those harmful gases in the air. But when we have too much of that fossil fuel gas in our air, it can combine with rainwater to create acid rain. So acid rain is usually when there's too much coal in the atmosphere, too much coal being produced. All of the excess is going to be rise up in the atmosphere. It'll combine with our clouds, with our rain, and it will rain out acid rain, which can be incredibly harmful to us and also a lot of plants and animals. And then we don't need any more greenhouse gases. We're already struggling with this global warming, our burning of fossil fuels increases the amount of CO2 and methane in our atmosphere, among others, which is very bad for our current state of climate change. So that's what I have for energy resources. So I just want to go real quickly. I just have a couple of slides about mineral resources. So we spent so much time on minerals. I know I don't have to get into it too much, but mineral resources are any mineral that's taken from the crust for our personal use. So for use by people for various things. So both metallic and non-metallic. So my personal favorite, the metallic mineral of gold, of course, is taken from our crust for jewelry, for money, also silver, lead, aluminum, iron, things that we build, things that we rely on, those metallic minerals. And then we also rely on quite a few of the non-metallic minerals, more for construction, for building. So building stone, gravel, and then also creating chemicals that we need. So halite for salt, for example. So if you ever hear of native metals, we're referring to metals that occur in their natural pure form. So minerals that grow filled with just that atom. So something like gold, silver, copper, or iron. Those are minerals that grow just as themselves. So they don't need anything else. Copper is just going to grow as copper. It only is consisting of the metal atoms. So full copper is just copper. We also have what we call ore minerals. So ore minerals are minerals that have a high percentage of metal, and the metal can actually be extracted. So the native metals are fully mineral, that 100% that mineral that you want to use. Ore minerals are minerals that have a high percent of that mineral you want, so you can actually extract it. So the ore is a different rock that has a high percentage of the mineral you want. So for example, here I have ores of copper. So the percentage of that useful metal, for this example is copper, tells us the grade of the ore. So something that is a high grade ore mineral has a large percentage of that useful metal. So for example, native copper, so this is just full copper, 100% copper, of course has a high grade. Whereas malachite, which you all identified in our, I think maybe it was our first mineral lab, you identified malachite. Our samples do look like this. It's the teal one. So that is an ore of copper, but it's not a very high grade. So it's only 57% copper. So it's not a hugely high grade ore mineral. So you'd want one of the other higher grade minerals if you were trying to extract copper from these rocks. So ore deposits, so rocks being the ore rock that's filled with the mineral that you want, the useful mineral as we call it, we'd call this an ore deposit. So ore deposits are formed in very specific situations. So one being near magmatic activity. So ore deposits can form from a cooling pluton. So if you have a cooling pluton that has that metal in it, the metal is generally heavy and will sink to the bottom, and you'll be able to extract that high percentage of that helpful or useful metal from that now cool pluton. Also, you can use hot water. So any hot water, hydrothermal action can actually, can cause that breakup around your area. It can also, let's say you are underwater at a mid-ocean ridge where you have a lot of heat coming up from the center, or from that mid-ocean ridge there, you're actually going to have a high percentage of ore deposits that will be right around your mid-ocean ridge because the ore minerals are generally heavier. The useful metal minerals are heavier, so they're going to sink to the bottom, where the other minerals, the other pieces of rock are going to be brought upwards with the hot water. So the hot water from your hydrothermal vent, from your mid-ocean ridge is going to move up because it's hot. That will bring a lot of the lighter elements up with it. The heavier metal elements, the ones that we're looking for here when we're talking about ore deposits, will generally sink down because something like gold is quite heavy. So sedimentary rocks sometimes also have ore deposits. So this would be like the banded iron formation. So when we have layers that form of iron, that iron will stay behind. It can sometimes be oxidized. That's when it's going to create the banded iron formation. A layer of iron can actually form within our sedimentary process, and we'll be able to go in and take that layer out, extract all of the ore from that, extract all of the iron from that layer. Weathering also allows us to make use of our ore deposits because, again, the metals, the metallic metals that we're looking for are heavy. So the heavier metals are going to stay behind while other things are weathered away. So the silt and the clay and the other less useful minerals will be weathered away, leaving behind the aluminum or the iron or the copper that you're looking for. And then the last one we call placer deposits. So this is, again, thinking that our mineral resources are heavier. So the minerals that we want are heavy. They're going to stay behind, say, if there was a river. The lighter minerals are going to be washed away. So I have a picture here that makes it a lot easier to see. We have our ore veins. So here is our layer of rock that contains our ore material. As this material weathers away down into our stream, the water is going to erode away, weather away these pieces. The smaller, non-heavy metallic pieces, so the lower density minerals, are going to be washed away, washed downstream. And the really high density and heavier grains are going to sink to the bottom because they're too heavy. So something like gold is often going to be found at the very bottom of a stream because everything lighter will be washed away. So if you ever see a movie where they're panning for gold, they're usually in a stream. This is why. Because the mineral will find its way to the stream and it will sink to the bottom because it's heavier than everything else around it. So when we're mining for our ore materials, we usually are looking for igneous rocks because this is where that mineral will have the chance to grow and grow large. So generally you're looking for plate boundaries, for plate activity, and you can either mine in shallow ore deposits or deep ore deposits. So when you're shallow, it's less expensive, it's less dangerous. We call that open pit mining. That's really where you dig a hole in the ground and you look around. Whereas when you're looking to go deeper underground, you have to build an underground mine. So something like this, where you're actually going down under the surface and you can reach all of this ore material. You can actually reach and mine within all of this igneous rock. So this can be really, really dangerous and incredibly expensive. So an example like this, we have a gigantic open hole, which looks incredibly close to this very packed city. Our mining generally leaves really big holes on our surface, just like this one, and it also produces a really large amount of waste rock. So this here is an open pit mine. So this is one of the shallow deposits. So this is something where people are actually walking down and mining along these layers. So what happens is we've removed all of this rock. So even if only a small percentage of it is aluminum or gold or copper, I believe this is a gold mine, all of the rock around it has also been removed. So we call that waste rock. So we will have a large amount of waste rock that's created in order to mine any sort of ore material. So this generally is just dumped into piles. And because it's just rock, it has no soil, it's going to be an unvegetated area of rock, of boulders. So it's generally not helpful in terms of our environment. We can't farm there. We can't build there. It really is just a pile of waste rock. Also, acid mine runoff is when all of these materials that we've dug up, like I said earlier, gets mixed into our water flow. So this can be just raining on the area and then washing off the harmful toxins into our water sources, into our streams, which go into our rivers, which flow maybe into our groundwater or into our reservoir, into our lakes, things like that. So they can be pretty dangerous, especially if they're not done well, if they aren't done with proper restrictions. So mineral mining can be pretty dangerous but very lucrative, because generally those types of mines you're mining for your metallic minerals, which generally bring in a lot of money. We do also mine for our non-metallic resources, so slabs of rock for buildings, stone that can be crushed to make concrete, cement, asphalt, bricks, gypsum makes up drywall, and we need lithium to make batteries. So there's quite a bit actually of our non-metallic resources that we use every day that not everybody realizes. So both the metallic and the non-metallic minerals are really crucial to the way our society works. So here, I think is my last slide. It is how long will our mineral resources last? So this is the expected lifetime of the ore reserves that we know of at this point in years. So the iron that is left in the world is 120, whereas we have actually a good amount of iron in the US. So there's about 40 lifetimes, as they call it. So there's a lot of iron, there's a lot of aluminum, there's a lot of nickel. However, you'll notice it's not spread evenly around the world. So there's quite a lot of aluminum in the world. However, we have barely any here in the US. So there's a lot of trading that goes on with these mineral resources. So your lab today is going to deal mostly with the energy resources. So that is on Canvas in your week 11 module. So week 11, I think I called it Geologic Resources is the name of the lab. You'll also need a calculator. So I did give you access to the calculator that comes with Canvas. So I made sure that for the entire assignment you have the calculator there, and I made it a scientific calculator. So hopefully that's helpful if you don't have one at home. It's nothing too crazy in terms of math, but definitely don't bother trying to do that math in your head, not the point of the lab. So good luck. I hope you have learned about some of the reasons why geology is so important, not only because it's interesting and because we can learn about the past, but because quite a bit of our society actually relies on our understanding of geology and our understanding of these resources and how they form, and knowing what is renewable versus non-renewable, and also knowing how non-renewable are those non-renewable resources, which at this point we know, we're running low. So good luck on the lab. Don't forget to talk to each other in the discussion, in your lab group discussions. I'll answer questions there, and I'm also available by email, of course. So have fun with the lab, and I'll see you next week.